All right, it's running.
Okay. Hello, welcome. Yeah, we can get started. Welcome. My name's Patrick.
I'm AJ.
We are going to be talking today about 3D printing, design for 3D printing, the additional considerations that you need to go through, and the future of the technology, innovations in the space, and like how it all ties into the goals that we're trying to promote here at Google Developer Club. So, like I said, this is like an intro to 3D printing technology. 3D printing is like, how many people have like heard of 3D printing? Everyone, basically. It's very well known, especially in a tech school. But the thing that kind of we want to focus on today is that it is, a lot of you have probably seen it in kind of hobby scale and a very unfocused scale where it's more hobby based and things like that. But we want to focus on 3D printing as a new form of manufacturing. 3D printing is a manufacturing process where layers of materials are deposited precisely by computer-controlled machines, and that causes a shift in the type of manufacturing you can do with the technology.
Alright, so I'm just going to go over some of the common types of printers, some different materials, and some of the different kind of printer designs that are out there. So the two most common printers are FDM, or fused deposition modeling printers, or stereolithic, I don't know how to say that, SLA printers, as on the right there. So the FDM printers are very cheap and easy to print with. Pretty much anyone can just go out and buy one and use it. I've got mine running up front there. They do have, they're pretty easy to use, and you can make, model, and prototype parts very quickly on them. They do have some downsides, like they're not as fine resolution on the print quality. You can see a lot more of the layer lines. They are very prone to temperature fluctuations, and on some of the materials that we will be covering, that can cause some issues in the print quality. And there's quite a large number of moving parts on FDM style printers, so lots of things kind of wear out and break, and you need to replace those. For SLA style printers, as pictured on the right there, that is, or also known as like resin printers. They have really tiny resolutions. You can print at less than 25 microns in resolution, so you can get really fine, really detailed parts. And they have lots of smooth surfaces that can actually rival some injection molded parts, so they're very good for high quality prints. However, resin is pretty brittle and can break pretty easily, and it is quite expensive, not only for the machines, but also just for the actual resins in those machines as well. So next I'm going to go over some of the common types of materials that are out there. There's kind of the big three, which is PLA, ABS, and PETG. So PLA is pretty much what, if you're going to start out 3D printing, you're going to be using that. It's a lot better for aesthetics rather than actual mechanical functions. Some of the pros of PLA is it's very easy to print with. You're probably not going to clog like your nozzle, as you will with some of the other more abrasive materials. And you can still do it on like a stock brass nozzle rather than upgrading to a hardened steel one. It's fully biodegradable actually, so all of these like PLA parts that we have, you leave them outside or whatever, that's fine. They'll break down, and you find they're actually made from corn. And it's very cheap. It's only like $15 to $20 for a roll of filament for PLA. However, they are very prone to heat deformation because they do print at a very low temperature. So anything around 60 to 70 degrees Celsius will actually melt and deform some of the PLA parts. And they're very brittle material, so if you need any high strength applications, they will just kind of crack and break under pressure. Next, I'm going to be talking about ABS. In the middle there, lots of common household items are made from ABS. Pretty much anything plastic in any devices you buy, or Legos, are all made from ABS. They're very strong and tough. It's a very strong and tough material. It's very durable to impact. It's very impact resistant, very heat resistant. It's very suitable for just things that get used every single day. You print like a phone case out of ABS, and that thing will stand up to the test of time, and it won't break down like PLA or PETG. However, it is very difficult to print with, not only requiring a high printing temperature, but it also releases quite a large amount of toxic fumes while it's printing, so an enclosure or a filtration system is absolutely required. It's also very sensitive to temperature changes, so even like the slightest draft of wind can actually knock your print off the print bed and cause it to crack and break. And UV light also makes ABS extremely brittle, so if you leave it outside for any longer than a day or two, it'll start to degrade and break down and won't be as strong as it used to be. The last material is PETG, and it is actually a food-safe filament, so if you're printing anything that interacts with food, like let's say a cutting board, if you want to print a cutting board, you can actually print that in PETG and it will actually be food-safe. It's very temperature resistant, requires quite a high printing temperature, around 260 degrees Celsius, so it's a very temperature resistant part, and it's again very durable and highly impact resistant, similar to ABS. However, the PETG tends to kind of deform and move a little bit, whereas the ABS will eventually just shear rather than kind of deforming with any of this like impacts or anything. However, it, again like ABS, it is very sensitive to UV light and will break down if you leave it outside for a long time. And it's very prone to stringing when printing, so it's very difficult to actually get printed down. And it's also a hydroscopic material, so that means it absorbs water, so you have to print it in an enclosed area where it is completely dry, something like a dry box. Some of the more uncommon types of filaments out there, we have glow-in-the-dark filament. So if you want to print anything that can glow in the dark, you can do that. We also have wood filament, which is essentially wood infused with plastic in the filament. So you can kind of lay down a mixture of wood and plastic, and you can actually burn off some of the plastic to just be left with like a wood part. Similar to metal, actually, there's metal-infused plastics as well, and you can just burn off all that plastic to just be left with a metal part. We have multi-material filaments. As you can see in the middle there's a Benji printed in several different materials, all on one printer. Usually you want either some sort of filament swapping or multiple nozzles for that. And on the far side, we have carbon fiber infused filaments, which we actually have a part up there in the front you guys can take a look at later. That is printed in carbon fiber, and it's when carbon fibers are kind of interwoven into some of the plastic blends. So you can lay that down as you're printing. So next I'm going to go over the three most common types of printer frames. There's the Cartesian style, the Delta style, and the Core XY style. Most printers that you will buy or see are actually a Cartesian style, like mine up front there. This is where every axis has one movement rotation. There's one way for Y, one way for Z, and one way for X. The Delta style frame has all of the motors kind of work in unison to make one movement, so you can do very complex, quick, precise movements, kind of zigzag back and forth very quickly. And then Core XY is kind of a complicated setup where some of the motors, if you turn just a singular motor, the carriage will actually move diagonally instead of like straight as it would on one of these machines. And all the motors kind of work in unison, similar to a Delta printer, to move the carriage around and print. The only difference being that Z is included in the Delta, and Z is a completely separate kind of axis on the Core XY machines. So yeah, again, Cartesian, very cheap, easy to make. Delta and Core XY are fast and more precise.
So that is obviously 3D printing from a hobby side. If the individual is going to get into it, they're going to get kind of a desktop 3D printer, and those have been increasing in both, increasing in popularity and decreasing in price for around the last decade. But the real potential with 3D printing and how it can really affect you in terms of a career or something like that is in the changes that it does to manufacturing. So traditional manufacturing, you kind of have two modes of, you can either form material, add material into something, or you can take material away. So on the left there's CNC machines and lathes that are going to take material away, and then there's plastic injection molding. And so the infrastructure in order to do these manufacturing processes is really big. You've got to have a lot of heavy equipment, you've got to make molds, you've got to have experienced technicians that are going to build these intricate parts for all these engineering designs. But with 3D printing, it offers a huge amount of opportunities, but then there's also considerations that you need to do when designing for 3D printing. this is an example of just something that you can design for 3D printing. When you design a part, obviously one of the most important things is that it's probably going to be made up of multiple different parts, and that those are all going to have to be put together. And so there's a lot of companies doing really awesome innovations with 3D printing, and how you have to consider how things go together much less. You could print this entire system, barring some of the springs maybe and things like that, in one section, right? So things can, because you're going layer by layer, adding in material, you can build things inside each other and reduce the parts of your components dramatically. Designing for 3D printing. When you design, you want to design for your manufacturing process. A lot of the times you want to keep in mind the limitations of your process. And so designing for 3D printing means that you have to take into account the physics of your machine. Plastic, it's melted plastic being formed into things, and it's going layer by layer. So you don't want to have massive overhangs that are going to force your plastic to have no support on the bottom of it. You don't want to have, or you do want to have, rounded edges. Rounded edges are going to be good in any part because they smooth out force, forces being applied. But they also make more gradual slopes for 3D printers that have better catches. This is an example. The pictures there are an example of two things, both from the research lab I work in. They are both holders for a battery, a lithium-ion battery. One is very badly designed for 3D printing. It's one solid piece. It's a skeletal design. There's no real way to print that and not have a totally horizontal overhang somewhere on the part. And 3D printers can compensate this. They can build supports and things like that. But if you're designing properly for 3D printing, you're not going to have any supports built on to your part. That should be your goal when you're modeling things like that. The one on the right is much better designed for 3D printing. It's in two halves that can both be printed, so there's not going to be any overhang, and then they can be combined after. So that's just kind of that theory in practice. Very similar, designing for production and how you lay out the pieces that you are going to print. These are pictures of 3D models inside a slicer, and we'll do a demo of that real quick. But I wanted to demonstrate that how you lay out this part, keeping in mind that the layers are going to be going up. One of them is going to have a lot of overhang, and one of them is not going to have any overhang, and you can save time on both of it. Another thing about this slide is that, because you're layering your piece, the forces that are applied to the piece are going to affect the piece in different ways. So if you know that this hanger is going to, have a force down, you don't want you don't want to print it like this, because this has the layers going in the same direction as the force, and so you get shear force that it's going to break much more easily along the shear than it is along the perpendicular to the shear. And so keeping that in mind when you're printing things, and keeping that in mind for how you're designing things, doing force analysis on 3D printed parts is really difficult and not a perfect science yet, because you not only have these different directions, but you also have infill. The part is not completely solid, and you have different varieties of infills, different thickness of walls, all settings that you can play with. And so doing force analysis on them is a little bit difficult, and you've got to take that into account when you're designing. Side note for resin printers, SLA printers. In the case of an FDM printer, you have a nozzle that's going around individually laying every single bead of material. With SLA printers, you don't have that. A lot of the way those work is they have a LCD screen that will light up UV pixels that will then freeze the resin in place, which means they do one layer all at the same time. And so the best thing you can do for if you're working with those machines is to load up the print bed with as many things as you can fit on it, because that's how you're going to maximize your time. And so designing parts such that they can be fit if you know you're working within the constraints of a specific machine is also something you want to keep in mind.
Alright, so I'm going to talk about the just kind of your average workflow going from a CAD model to a finished design. So first off, you successfully designed some part in CAD, so you're going to export whatever file type you want, STL, OBJ, whatever. And next you want to think about exactly what is this part going to be used for? What printer will suit that best? You want to pick the best printer. Is it something that is just aesthetic, so I can just print it on a PLA, out of PLA, on just a basic FDM printer, or does it need to be something extremely rigid, and I need to print it on ABS, on an FDM printer? Or can it be something like a special type of material, like a ceramic or glass part? Do I need to use an SLA printer? So once you've made that, then you want to kind of think about your material choice too. You know, exactly what brand, filaments differ from every brand, even brand to brand, or batch to batch in the same brand, filaments vary. So you want to think about exactly what are the properties of all the filaments that I'm going to be looking at, and which one will best suit my part. For something aesthetic, you want to use PLA, but for something that's practical, like a bracket on a car or something, you might want to consider either ABS or PETG. And that kind of goes along with the part requirements, you know, exactly how big is that, where is it going to be used, all those things you want to keep, in consideration. So after you kind of have all that, jotted down in your head somewhere, you want to import that part into your slicer, and you want to kind of start messing around with the parameters that you're going to use to print it. You know, which orientation is going to be the best orientation to have the most amount of strength for the application this will be used for. How many walls do I want? How much infill do I need? Does this need support material? And so once you have all that done, you can just go ahead and print your part. And some materials, kind of like ABS, you can actually do some post-processing where you can smooth all the layer lines out using acetone. All SLA and resin type printers need to have lots of post-processing where you actually cure the part in like a UV chamber. So you need to kind of do all that post-manufacturing on your part, and then once you have your part, you want to start testing that, and like, okay, now that this is broken, how do I fix this? How do I design this better? And go all the way back to the start and keep iterating through this until you get your final part for production and whatever you need.
A manufacturing workflow like this is going to be similar, obviously not the exact same for a lot of different things, but the power of 3D printing is that you can go from this to that in maybe 20 minutes depending on your part. There are some parts that take much longer, but at most, you can go from model to testing to remodeling to testing to remodeling to testing in one day, which changes the prototyping space and allows for really increased speed of innovation. Now we have there's a live demo of a printer going, but we also have a slicer to demonstrate and just show what those what that software looks like. Each printer that you work with is going to have a different sort of thing. This is specifically working on Prusa Slicer, which is from the specific company Prusa, and it is currently programmed for the i3 MK2S, which is my printer. And so you're going to get this test bed that you place your parts on. You can import. I'll do this over my shoulder without being able to see anything. You can import parts as saved as an STL, OBJ, those file types, and both place it on the bed. You can orient it. So if this part came into the slicer, at a 90-degree angle, I would definitely want to move it around because that's not a viable orientation to effectively print something. In addition, there are parameters and a whole bunch of settings. You can very minutely play with the settings of your printer. You can change, the temperature of a variety of different things, including the nozzle and the bed. This is all obviously specifically for FDM printers. You can change wall thickness, extrusion speed, rate of movement of the printer itself. Anything with a motor and a sensor, which is most of the printer, you can play with and you can change in this for filament and printer and everything like that. And so these parameters, like Prusa Slicer is very good. There's some proprietary ones out there that don't let you do this sort of thing. But you can tune everything on your printer to give you the best quality parts, which is also going to speed up your manufacturing time. And doing this tuning is still easier than doing it on a full machine a full CNC machine that is going to take longer to program and take longer to implement your piece. So this is an example of one slicer. There is also this, which is Elegoo's Cura. So like you can just see this is going to be the general layout when you bring something in. You are going to be placing your object down and manipulating it in here. After this, you generate code. This is what tells the 3D printer what to actually do. And you can actually go through and examine the individual layers of the piece as it is going to be built by the 3D printer. And this gives you a lot of ability to see, is this going to fail before I even put it on the bench? And you can change infill and stuff from here right in this slicer, so you don't have to print it and then realize it failed. So yeah, anything you want to add?
I think that pretty much covered it.
So now we want to talk about some of the emerging technology, because this field, like I said, has just so much important potential for things we can do in the future.
Alright, so first off, I'm going to talk about some of the ceramic 3D printing. It's relatively new. Essentially how this works, it pretty much only works on SLA 3D printers, it's the resin-based printers. What you do is you take this kind of ceramic and resin compound. It's about 80% ceramic, 20% resin, and you can print that layer by layer on an SLA printer. And then once that part is done, you can anneal it for several hours at a very high temperature to burn off all that resin, and you're left with a pure ceramic part, which is used here by demonstrated by Formlabs as like a rocket nozzle. And ceramic parts are really useful because they are very high temperature resistant, so they can do insanely high temperature applications, a lot more than something plastic like ABS or PETG could do. So, yeah. And
there is also new innovations in loose media printing. When we talk about filaments here, that filament has to be a specific diameter, it has to be a specific tolerance. That is not going to be something that is achievable in a lot of different places. And so the idea of being able to kind of almost combine an injection machine with a 3D printer and get this ability to put loose medium into a 3D printer and get a finished part in minutes is really industry changing and world changing in terms of the speed of design and innovation that can happen.
yeah, and you can actually also 3D print with glass. As of right now, there's kind of two competing technologies for glass 3D printing. On the left here, we have an FDM style glass printer, and on the right, we have the processes of a SLA style glass 3D printer. The printer on the right essentially just superheats a bunch of glass in a chamber, and that chamber gets pressurized and forced out of the nozzle at high temperature. That was actually developed by MIT. Whereas the SLA style printers are similar to the ceramics, where all the glass particles are kind of embedded inside of the resin. And once you print that and you burn off all the resin, as shown by the process on the bottom right there, you can just be left with a solid glass part. And glass 3D printing allows for lots of new and almost seemingly impossible ways, like geometries, to make glass parts. And it's used a lot in circuit board design as insulation, as you can kind of cover certain areas of a circuit board in glass and do that very, very smallly and accurately.
I also came across a paper the other day that was talking about 3D printing VR lenses, so that's super interesting. You can get a lot of the, there's a company I think that's also doing glasses lenses, and so the manufacturing for those is pretty intense, and being able to 3D print them is a lot simpler. In addition, there are multiple companies that are 3D printing rocket engines, which I think is one of the best illustrations of the potential of the technology. You have Relativity and Rocket Lab. Relativity is working on 3D printing their entire rocket body with completely automated manufacturing systems. While Rocket Lab has designed their own rocket, which is, I believe, the Rutherford, which is, again, completely 3D printed. And like I said in the beginning, where before you have designers who some of their main focus is figuring out how technicians are going to put these things together, and they don't have to think about that anymore because you're going layer by layer, and everything is supported by itself, connected to itself, and you get a incredibly functional piece of technology with a lot less parts. And I think that's really illustrated by this, which is something taken off Relativity's website, where you have traditional both factories and engine systems that have over 100,000 parts, 2 years to build, with a very complex supply chain, whereas with 3D printing, you reduce that part count to below 1,000, and it takes 2 months to build things. Rocket Labs, the company over there, not only are they 3D printing their engines, they're also carbon fiber weaving their rockets, and their goal is to be able to build a rocket in 24 hours, which I think they've reached at this point, but I'm not sure. And so, it's just such a rapid development that you would have never thought possible with traditional manufacturing techniques. And that leads into what is the big picture and the big takeaway, and why is 3D printing more than just a desktop hobby sort of situation? The first thing is all-in-one production machines. Before 3D printing, you needed to individually create molds or die casts or steel stamp plates for anything you actually wanted to build. And now you have one machine that can build, that machine can make so many things. The main requirement is it has to fit within a 250 by 250 by 250 millimeter cube. And so, there's a lot of, in space, this is, hugely major, especially with the loose medium, where you can take in situ medium from other planets or moons and 3D print with that automatedly, because getting materials up into space is so difficult and so costly. Let's make one machine that can be an all-in-one manufacturer for a variety of different things that we could do in space. And so that's super awesome for the future. The next thing is a just general democratization of manufacturing. This part here is so complex. It's probably maybe an electronics mounting or something for a motor or something like that. And there is no way a hobbyist could dream of making something like this 15 years ago. But I can go home and print one of these things and implement a truly, well-engineered product into a design because of this democratization of manufacturing. Anyone has the ability to do something like this because of the decreasing cost of this technology. This has a lot of implications for both new designs, but also for fixing things. You're no longer necessarily dependent on a company to provide an exact part that can fix something. This is taken out of a research paper done by TARS here at Clarkson, where they 3D scanned objects and then broke those objects and then 3D scanned them again and could 3D generate new replacement parts for them to be 3D printed and fit perfectly into the broken parts. And so you can't do this with any other manufacturing technology. To do this with something like plastic injection, you would need to perfectly generate the 3D model, but then you would have to go and find a way to plastic inject that or fully get a several tens of thousands of dollar machine to intricately carve out the piece. But with 3D printing, it's much simpler, and one machine can do a variety of different things as opposed to one highly specialized machine for one part. This brings me to the conclusion, and we wanted to talk about the first project that we want to do as Google Developer Student Club. We want to integrate a lot of new technology and things into our development and be a very project-oriented based community. And so we wanted to integrate 3D printing design with robotics and programming. This is going to be a project that is totally open to anyone who wants to join. And it's just, our goal is to just pick something that we can all learn from and that we can all, build familiarity with technology and things like that. This is pretty open. The kind of pitches that the eBoard is considering is something that is pretty small scale, integrates both hardware, electronics, software, as well as 3D printing and things like that. So these are kind of small scale projects that can be made on a desktop 3D printer with funding from the club or Google or things like that. So if this is interesting to you and you want input on these projects, then definitely reach out and talk to one of us. But yeah, thank you guys.
So if you guys have any questions or just want to come up and take a look at 3D printer, feel free to do so now. We've got a bunch of different examples of 3D printed parts. So just come up, take a look. If you have any questions, just let us know. Thank you.
There's a hand.
There's a hand.
Is this TPU?
Yes, this is TPU.
It's very strange. As is TPU.
The boat doesn't like.
It floats very well. I don't know. That is a carbon fiber part, actually. That's a TPU. It's currently going around the nose of the skateboard, so you don't destroy it.
What is this from?
That's a Raspberry Pi. I used to use it as.
Is that a Pi too?
It's a Pi.
Raspberry Pi.
It's a Pi.
I used to use it as the web server for my printer, but I switched over to a Pi 3. There's also a Raspberry Pi 0 out there too.
Do you ever use it?
Yeah. I used to use it just as like a monitor. From a very old project.
Is this the carbon fiber connect to the?
Yeah, for the drive.
Yeah, for the drive.
Yeah.
That was the one that was accidentally printed with way too much infill, so it's a lot heavier than the actual one. And then those are just some cable clips that I have.
Can you 3D print a 3D printer?
I mean, yes, actually.
Yes.
That was the whole goal of the RepRap project.
Yeah.
What project?
RepRap project. That is the project that kind of created Marlin, which is the software that most 3D printer boards run. So it's like a fully open source interpreter. That's just a base. We're not printing out
It's
everything.
actually a shot.
I don't know if it's watertight, so.
But yeah, you guys are free to hang out or head out, whichever.
Yeah.
Oh yeah, you probably should tell them about this.
Yes, that is hairspray that I use for meditation. It's the extra cold stuff, the worst ones. Especially now that the coating on it is like gone.
What is this for?
What?
Just like,
I don't know, it just controls the speed.
I like how you have this so that you can sleep at night.
Yeah, that's why I built
It's
this.
a major issue I have with mine.
That's why this thing is like completely silent, because I like to sleep.
This is very cool.
Yeah, honestly, that came out really
That's
well.
really nice.
That was really almost no
class as well.
Yeah.
I just threw in my new board.
Going good, going.
It's good.
Anyone got any tests coming up?
I had one yesterday, and I'm still riding the high of it being over.
I have one in statistics next week. I'm not sure. Which I think is after break. So.
If you guys were going to do a robotics project, we would have to talk to the director of the CS department, like Maciel, and get a bunch of parts and talk to Sean about that.
I think we just need a couple, like, at least for the one on the left, we just need like a couple.
Would you guys be, what kind of project would you guys be interested in like doing? Because we can do pretty much anything. It just depends on what you guys want to do. If anything pops in your head, just put it in the general chat.
At any scale too, these are very small, for the purposes of introduction and demonstration, but there is a open source spot from Boston Dynamics. There's a team making an open source one of those, and I really want to build one at some point.
I'm getting a Kickstarter for this quadruped dog robot thing. It should come sometime this month. So maybe we could do something like that. It's open source. But probably if we want, we can get more parts for that after it arrives and then we can modify it. Make it the Google Doc.
That sounds incredibly sinister. But yeah, you wanna, is the recording stopped?
Okay, we should probably stop that.
I don't know how to work your camera.
It is